Alright guys, at this point I realized during editing, I forgot to unblank the screen like an idiot. So, let's begin doing that right now. As of recording this video, I think it is 11:03 p.m. But we still got this. We still got it. Don't worry. Don't worry about it. Don't worry about it. So, number 1. So this one's pretty simple. Simple pendulum. It's just a bob of mass 1.8 kilogram attached to a string of length 2.3 meters. This pendulum is held at an angle of 30 degrees from the vertical by a light horizontal string, which you can ignore the mass of the string. As shown on the figure, draw a free body diagram. Okay, very cool, right? So, let me unblank the screen before I do something stupid. I'm going to do A and B, where once you calculate the horizontal string tension as well. So, let's start off with that free body diagram. You've got FT1 right there, FT2, and MG. And this is 30 degrees. So you've got the cosine of it and the sine. So now we're on to part B. Figure out the tension in FT1. So this is using simple trigonometry. So you know that sigma F sigma F of X equals FT1 sine, this is sine 30 equals, because this is not accelerating, it's equal to each other. So equals FT2, right? As it goes to 0. So because it's not accelerating in the y direction, that means the vertical component of FT1 is equal to mg. So using some simple math, FT1 equals mg over cosine 30, right? And now to find FT2, you just sub that in, right? And you get mg tan 30, and you plug in your values. Pretty easy. Alright, now on to question C. Horizontal string is now cut close to the bob and the pendulum swings down. Calculate the speed of the bob at its lowest position. So right now you have the bob at point A, and you want point B. You want a point B, right? So you need, what is it? This and that. And it's just the difference. And so you're given that the string is 2.3 meters right here. So 2.3, and you just do some simple trig. 3.3 cosine, what is that? Let me just check that really quickly. Okay, sorry, I wrote this wrong, but we can just apply it here. Cosine 30. I can't be bothered, I'm sorry. So now you just do some simple math and you get like 0.3, right? And using conservation of energy, so kinetic energy equals mgh, gravitational potential. Divide m out, and now you get v equals square root 2gh. So you take that over there, square root, bam, bam. Okay, you got this. And now you just plug in your values. So 2 times 9.8.1, or 9.81 times 0.3, and you get your answer. Alright, nice. So now on to number 2. Let me show that. A roller coaster ride at an amusement park lifts a car of mass 700 kilograms. Is it 700? Yeah. To a point A at a height of 90 meters above the lowest point on the track as shown above. And you get your like point A or whatever, right? So A1 says indicate the figure the point P at which the maximum speed of the car is attained. And that's at the bottom of that little slope because you're right. At that point, you've converted all of that gravitational potential energy, that's your lowest point, right, into kinetic energy, which is 1/2 mv squared. So 1/2 mv squared equals mgh. Pretty simple there. And let's visualize that for you guys. So, bam, bam, right? So it's this point right here, point P. And let's just draw these really quickly, because I don't want to write that again. So the maximum speed is literally just that formula we did in number 1, v equals square root 2gh, and h at this point, at point P, is 90, so 2 times 9.8 times 90. Super easy. Take the square root of all that and you get your answer. And the next one says B, calculate the speed VB of the car at point B, and then you just have to plug in your differences. So you know this is 50 meters and this is 90, right? So it's literally just 90 minus 50 equals 40. You plug it right back in. Super easy. And now it says C. What is it? At point B, draw a free body diagram of the forces. And this is Fn. This is Fg. Pretty simple because there's force gravity pointing down, and that the track is exerting normal force downwards too. And now you have to figure out, the forces on that free body diagram and the magnitude of them. So you know that Fg equals negative, well, I can't be bothered, so let's not use negative. It's magnitude, I lied. 9.81 times 700 kilograms. And I can't be bothered to do that math, but that is 6,860 newtons. And now you get, shoot, I'm running out of time. My battery's running low. Equals F of G plus Fn, and using simple math, you get Fn equals mv squared over r minus mg. Then you just plug in your values and do the math, because you're already given your height, whatever, right? And you get about 20580. Congratulations. And you use your answer from B in order to calculate that. Okay, next question. Please tell me I did not leave that. Okay. Next question. Number 3. So this is 4 parts. So you got this guy pulling a 100-kilogram box, right? And yeah, we're just some basic differentiating. Okay, whatever. Derivatives. I'm too tired for this. It's 11:13, man. So A wants you to determine the speed of the box at time t equals 0, right? So you just take the derivative t cubed plus 2, is that 2t? Yeah. And that is 1.5 t squared plus 2. And now vt equals that, whatever, very cool. And you just plug in your values and you get, since t equals 0, you get 2 meters a second. Amazing. So let's write that formula down here for future reference. Okay, so kinetic energy, so that's 1/2 mv squared, right? So you just plug in your values for B, where it asks you to solve for kinetic energy of the box. So 1/2 of 100 is 50, right? And then you just plug in your equation, and boom, that's B. Okay, so now number 2, net force acting on the box, and you need to take the derivative of this again. So AT, I'm not gonna, it's like really simple math. So 2 times 1.5, which is 3, and you take that, it's n minus 1, so 3t. Pretty easy, you drop this, and because force is equal to ma, it's literally just 100 times 3t. So F equals 300t. Pretty simple. Alright, so power delivered to the box, this one's just F times V. So basically 300t times 1.5t squared plus 2, because power equals F times V, force times velocity, because it's the rate at which work is being done. So it's Fd over T, which gives you Fv, right? So you just plug that in, you get your amazing answer of 450 t cubed plus 600t. Super easy. Okay, so now calculate the net work done on the box in the interval 0 to 2 seconds. So this one, you just plug in your values here. 1.5 2 minus 0 squared. I just don't want to do this, man. And you get like 4, something like that. 4 times 1.5, 6 plus 2, 8. That's not right. Okay, you know what? Maybe I will have to do it the right way. Okay, 1.5 times 4 plus 2 to the power of 2 minus 50. That's 0 plus 2 squared. So that's 50 times 4, and then 5, 6 plus 2, 8, 64, so 50, 64, which equals to about 300, sorry, 3,000, I lied, 3,000 joules. And part D is whether the work done in the interval from 0 to 2 would be greater than or less than the part in C. Let's see here. Work done on the box by the student in the interval 0 to 2 would be greater than or less than. And it'd be greater than because there's a frictional force opposing. And yeah, that's about it. Thanks for tuning in, guys, and we will see you tomorrow. Well, actually not tomorrow, because I've done the homework mistakenly, sadly. On the first video, I was like, dude, pain. Okay, well anyway, see you guys.